Okay, so today we're going to talk about cosets and factor groups, and I'll try not to be self-conscious about the fact that I'm recording, but I will have to speak clearly because my microphone is not the best. Let's make it a little bigger. All right, so I'll go through these starred problems, and you can ask me questions. And let me go to OneNote. So the first one I was going to do is 1017E. So let me put that on my OneNote here. Okay, and I'll make that bigger so you can see it. And I should just be able to clip it and put it on the screen. Let's see if I can do that. Need to get to my book. So 1017E. Okay. All right. So here we go. All right. So let me clip it. All right, so let's copy this. Whoa, that's huge. Whoops, too much. Okay, and then let's make it small. All right. So it says list the left. Is it up yet?
Yes.
Okay. So very fast response. List the left and right cosets of the subgroups in each of the following. Tell whether the left and right cosets are equal. So presumably you have some background on what coset means. Now, I can tell you where in the chapter, maybe I'll be able to clip this, but the definition of coset is back here. We'll just clip this one too. Let's see how this works. Okay. I think it's getting bigger and bigger. Oh. So let's think about what coset is. All right. So the left. So you have to have a group and a subgroup. A group and a subgroup. So imagine a big group, a little group sitting inside a big group. So for example, let's just take one example. The integers is a group. And the multiples of 4 is also an additive group. Right? So you've got a group sitting inside a group. So the left coset of H with representative G is defined as the following set: GH, which is the set consisting of GH for all H and little h. So in the case where, let's say, all right, so I'll say example here. We'll say G equals Z and H equals 4Z. Okay. Now, since this is an additive group, instead of writing GH, we'll write G plus H. Right? A plus is the group operation. Or yeah, maybe we should pull up a chair and see. Otherwise, it's not going to. And they've got two screens over there. Or you can join me right here if you want.
Actually, I can also log in up there.
Yeah, you could do that. That would work. Yeah, I didn't even think of that. That's super. All right. So we can look at little g is an element of big G, which in this case is the integers. And H, the H you think of as the set, the whole set of 4Z. Okay. So we'll look at 0 plus 4Z. Now 0 plus 4Z, you can simply write it. The definition says that's the same thing as 0 plus H, where H is in Z, is in 4Z. Now, if I was going to list out the elements of that set. Because you're adding 0, it doesn't change anything. So it's still 4z. All right, so you with me? That's still 4z. All right, now what about 1 plus 4z? So the definition says that's 1 plus h, where h is in 4z. Okay. So if I was going to list that out, what would those elements look like? Give me an element in 1 plus 4z.
1 plus 4z?
Yeah, in 1 plus 4z. 5. Sorry? 5. Yeah, 5's in there. Sure. Anything else?
9.
9. Okay, yeah. And you just keep going. Every 4. So 5, 9, 13, and 17, and so on. Okay. And then you go down to 1, and minus 5, and minus 9, and so on. Right. Whoops, sorry. Okay. Okay. All right, so you kind of get the concept, right? And then you can also do 2 plus 4z, and it's off the page, so bump it down.
I have a question.
Sure.
When you went down, did you go down 4?
When you say go down, what do you mean go down? Yes.
Numbers.
Oh, right, so that's right. So it should be minus 3. So thanks. Minus 3. Very good. That's some brownie points. All right. Okay.
No, I don't want to
All right.
down 4.
All right. Now, and you can think about that too, because minus 3 is 1 plus minus 4. Right? Minus 4 is something like that. So you're going to get 2 plus 4z, and also similar. That's equal to, you're going to start with 2, and then 6, and then 10, and so on. And then you'd also have minus 2, and go and so on. And you're also going to have 3 plus 4z. And then you have 3 plus 4z. And that's equal to 3, and then 7, and so on. And it also goes down. And minus 1. Okay. Okay. All right. Now, and then you can have 4. What's 4 plus 4z? So if I take everything in 4z and add 4 to it, you get back 4z. And so that's equal to 4z. And then 5 plus 4z. 1 is equal to 1 plus 4z. All right. So what you're discovering is that there's actually only 4 distinct cosets.
If you take the union of 0 plus 4z all the way up to 3 plus 4z,
Yes.
the set of integers.
Yes. Yes. So that's right. The union of all cosets is the entire group. Cosets of H in G is G. The intersection of any two cosets is what? Okay. All right. So something that I didn't do because we ran out of time before the break is point out that the cosets are equivalence classes. Or the cosets form a partition. Obviously, because they're disjoint and their union is the entire set. So that means the cosets are equivalence class. All right. So if you remember in number theory, we talked about that, and there's a connection there. And you might want to look back and see what we talked about there.
It deals with the equivalence relation, right?
Yeah. So you can say cosets define an equivalence relation. Yes. Yeah. You would say two numbers are equivalent if they're in the same coset. I can even write that. Now, what's kind of cool in this case is that Z is an infinite group, and 4Z is an infinite group, but there's only a finite number of cosets that divide up the group. Now, the other thing is that, note, the cosets are or are not groups. Which is true? Or so we talked about subgroups, right? Right. Cosets are or are not subgroups. Okay. The answer is not. Not. You could say not closed. You can say because only because they don't contain the identity. So make sure you don't. People trip up on that. Cosets are not subgroups. Only what you have got is one subgroup, and you've basically got copies of that subgroup. I think one of the examples that's later on, you think of a group as a loaf of raisin bread, and you take slices. Each slice has the same number of raisins. So the slices are the cosets, and the end piece is the subgroup. Only the end piece is a subgroup. All the other ones are copies of that subgroup. So you can think of cosets as kind of a translated copy of a subgroup. All right. So the question that I wrote here. Now the other thing I should mention is these are left cosets. These are all left cosets. So you could call these the left additive cosets. Now, what about the right additive cosets? They'd be the same because of commutative. All right. So right additive cosets are the same. Why is it so small? Okay. In this case, because Z is. Don't you like to use a fancy word? Abelian. Okay.
Fair enough.
Okay, because Z is abelian. So here I should underline in this case.
So I have a question.
Yes.
What would be the identity in this case? 4Z?
Well, the identity is 0.
Mm-hmm.
When you say the identity of what?
Well, for commutative it would be 0 because it remains the same, right?
Well, all right. When you say identity, you have to be talking about the identity of a group or a subgroup. So what group or subgroup are you talking about?
4Z is H, and H is in.
Yeah, H is a subgroup of G. So are you asking what's the identity of H?
Yes, sir.
All right, the identity of H is still 0.
Okay, but doesn't 4Z equal 0?
No, 4Z is all the multiples of 4.
Okay, I get it.
All right, 4Z is all the multiples of 4. Contains 0, but it's not 0.
So going back to that raisin bread.
Yes.
So the 0 plus 4Z would be the end of bread, right?
Yeah, one end.
Okay.
Not both ends. One end.
So the other end would be 4 plus 4Z then?
Well, no. See, that's the bad example. It's just don't think of two ends of the bread. Just think of a loaf, and there's one piece of that loaf which is maybe you should say that the slice in the middle. The slice in the middle is the subgroup. Okay. I didn't mean that there are two ends and the two ends had special functions. I just mean that there's one slice in there. There's just one slice in there that's a subgroup, and all the others are copies.
Oh, okay. Yeah.
Right. All right. So let me go back to the question here. The question that was asked was, List the left and right cosets of the subgroups in each of the following. So let me get left and right cosets, and the one I asked myself was 4e. So let's do this. So 4e would be, come on, go down. It's not giving me, oh, there we go. So let me snip that. 4e was the, come on, where are you? Here we go. Okay, go back here. Insert clipping. A4 and S4. Now A4 is the set of even permutations. Okay.
How do you know that?
That's the definition of A4.
Oh,
It said in the
okay.
problem. It says in the problem. Go up and
Yeah, I see.
go up and say. Okay.
No, fine. I shouldn't have walked out.
All right. Now, A4 is a subgroup. Oh, we've talked about that. Okay. Now we want to figure out what are the cosets of A4 in this. Okay. First of all, A4 itself is a coset. I can write A4 is equal to ID times A4. So A4 itself is a coset. Right. Now, how would you get, now here I mentioned that even permutations are a subgroup. What about odd permutations? Are they a subgroup?
Is it the odd, is it only 1? And the even is 0?
When you say the odd is 1, I'm not sure what you mean.
On the,
Well, give me,
Odd doesn't have the identity, right?
odd does not have the identity. So odd is not a subgroup. So it's not a subgroup. Okay. All right, but let's see. Could it be a coset?
yes.
Okay. How do we get odd permutations as a coset?
Adding odd permutation.
All right. So what's the simplest odd permutation?
One,
1,
two.
2.
Okay. Sorry.
Okay. All right. All right. You with me? 1, 2 is a transposition. It's a product of one transposition. So it's an odd permutation. All right. So let's consider this set 1 to A4. And what that is equal to, remind you what that means equal to. It's equal to 1, 2 times, can I do this? Where sigma for all sigma in A4. Oh shoot, it's not going to work. A4, we'll just A4. Okay. All right. So this is another subset of S4. This is also a set of permutations. So 1, 2 times A4. It's broken. Here, what I have to do, because I inserted an equation and it thinks it's still an equation. Maybe I can do this. All right, here, maybe I can do this. I'll fool it. I've had enough experience fooling this stupid thing. So, there we go. Okay, good. Okay. So 1, 2, A4 is a subset of S4. Now, let's think about this subset. Suppose you take a permutation in 1, 2, A4. Can you say anything about whether it's even or odd? It's definitely odd. Do you see why? Well, I'll rewrite that assertion, and we'll talk about why. Any element of this thing is odd because it can be expressed as a transposition times what? When I say times, I mean let's see. I'll say as the product of a transposition and. Now, it's the product of a transposition, which is the 1, 2, times some element of A4. What do you know about elements of A4? They're even, and an even permutation. Okay, and if you've got an even permutation, which is an even number of transpositions, and you add one more, that's an odd number of permutations. Okay. Okay, so what that's telling me is that 1, 2 times A4 only contains odd permutations. Another way of saying that is 1, 2, A4 is a subset of the odd permutations. Right. Okay. 1, 2. Let's see if it's still in my. Okay, it's still there. Okay. There's a subset of the odd permutations. Now, on the other hand, let's think about this. Take any odd permutation. Take any odd permutation. Let's call it, what should we call it? We'll call it mu. Now, my question is mu in 1, 2, A4? Here, let's do this. Let's paste this. Here, I think I saw it. Whoops, I don't have it in my buffer anymore. Right.
It should be, because you have all even permutations, and then you're making them all odd, but you're using the same permutation across everything.
Okay. All right. Now, in order to show this, I should be able to express mu as a product of 1, 2 times something in A4. Okay. So let's see. So I can express mu it's always broken again. One of these days I'll learn how to use this. I can express mu as 1, 2 times something. Let me just say mu. Now it's the other one. Equals 1, 2, but mu is equal to 1, 2 times what?
Mu to be S4.
Well, it has to be a specific element. It has to be a specific element, a specific permutation. All right, so let's do this. If you can't see what it is, let's just call alpha. Oops, sorry. And then we need to solve for alpha. Okay. Where did it go? Solve for alpha. All right, now, we've seen equations like this before. How would you solve this for alpha?
You take the inverse.
You take the inverse of which?
The permutation 1, 2.
Okay, yes, and what's the inverse of 1, 2?
1, 2.
1, 2. Okay. All right, you got it.
Okay.
Right? So you multiply both sides by 1, 2.
On the left side.
Yes, on the left-hand side. So 1, 2 on the left. And you'll get, just copy this. Well, you're going to get alpha is equal to, well, isn't this great? I just do that and move more there. Okay. All right. Yes. Okay. All right, so 1, 2 alpha equals mu. Okay, therefore, let me do this.
So an odd permutation goes with an odd permutation.
Okay, so that means that so mu equals 1, 2 times alpha, which is the same thing as 1, 2 times 1, 2 mu. If you look at it now, it looks obvious, right? Because the 1, 2's cancel. So I can write mu as 1, 2 times another permutation, 1, 2 mu. Now, is 1, 2 mu even or odd?
No. Yeah.
All right, so because we said mu is odd, and we're adding a transposition to it. So 1, 2 mu is even. Is even. All right, so what does that tell me? So that was a long way around. Here I said take any odd permutation mu. Right, so this was where I started, and here I said mu is equal to this. That was the conclusion. All right, now the fact that mu is 1, 2 times 1, 2 mu means that mu is in 1, 2, A4. So you can see why I did this problem instead of asking you to do it. The other problems are not this complicated. So mu is in. I'm never going to use mu again. I haven't figured out how to. Is in 1, 2 times A4. Well, here, so mu was an arbitrary odd permutation. Mu is any old odd permutation. Right. So on the one hand, we've said that any element 1, 2, A4 is odd. On the other hand, we said any odd permutation is in 1, 2, A4. So that tells me that the conclusion is that 1, 2, A4, no, not me, 1, 2, A4, sorry, is equal to the set of odd permutations. Okay. Now, question. How many cosets does A4 have in S4? How many cosets?
You want to do all of them?
Right. So I'm going to try to draw a bad picture here. Right, here's my S4. Here's my S4. And then here I have A4 sitting inside. Right. Okay. Now I also have 1, 2 times A4 sitting inside somewhere. This is terrible. I will remember my tablet next time. 1, 2 times A4. That's worse than terrible. Okay. Where's my mouse? Times A4. Now the question is there anything else besides A4 and 1, 2, A4? And the answer is no. There's only even and odd permutations. There aren't any others. So in fact, A4 has 2 cosets, itself and 1, 2, A4. So that's the conclusion. A4 has 2, I should say 2 left cosets, itself and 1, 2, A4. All right, now for the homework, part of your homework is to show how this argument, how does this argument change for right cosets. Well, yeah, but be careful because permutations are not commutative, so it's not automatically true. But see if you can carry this argument through to with right cosets. And Kat, can you get rid of the stupid green? All right. All right. So now the other questions in that were looking at the other ones like you're not seeing you flip back to the book and look at 10.1.7. If you look at the other questions in that exercise, text 10.1.7, those are exercises that you can actually list out the cosets. Now, for instance, part A, I don't know if you can, Kat, maybe you can show that on the screen too. Go to exercise 10.1.7 in the book. So go to the Explorer. Chrome is better, yeah. And if you type SL, I don't know how often you go there, but if you start typing SL2X, it may jump there. No, yeah, it's not there. So you'll have to look for. You can look at abstract algebra.alter. Oh, there it is. Third one down. And HTML. And down. This angle brackets, it's funny because in linear algebra we just saw angle brackets. Angle brackets was span. But now in this angle brackets means this means the set generated by 8. So, and if you think about what that is, that's going to form a subgroup. So you can figure out cosets manually and see how many there are, and do that for right and left cosets. So. That problem took us a while, but I think it's worth going through that pretty thoroughly. Okay. And all right, so let me go back to my assignment. Next one I was going to do was H of the same group. So let me look at that. So I'll make another page. This is 10, 1, 7, H. And where's the book? 10, 1, 7, H. All right, in this case, it's looking at T and C star. Okay, so let's insert. You're yawning. I'm the one with jet lag.
Oh, no.
Okay. Okay. All right. All right. So this next one, are you on the right page? I just created a new page. So we're looking at. Oh, I see. So it follows me. Or did you go there yourself? Okay. All right. So we're looking at T and C. Now T is the unit circle. We've seen that before. Come on, do something. Stupid thing. Okay. And the unit circle, just to remind you, the formal definition is equal to the set of complex numbers z such that the absolute value of c is equal to 1. All right. Now, when it says C star, what's the operation? Means non-zero complex numbers under multiplication. Okay. All right, now, so that means that when we find cosets, we're going to multiply t by something. So, cosets of t are sets of the form. Well, let's just say some complex number, let me just call it w times t, where w is a complex number. Okay. All right, so let's just look at some examples. Suppose w, let's do something simple. Suppose w equals 1. All right, that's a very simple example. Then wt is equal to t. All right. Whoops, what happened? Then wt is equal to t. Still gone. All right, let's try something else. Now you could try I. How about w equal to I? What happens when you multiply a number of absolute value 1 times I? All right. You do. Then let's just say we'll say it. What is it? It is it. Okay. So it is equal to the set of I times z, where absolute value of z is equal to 1. So remember, we can write so z is equal to, now remember, in polar form is what? What's the polar form of z?
Isn't that
all right, yeah. Because the radius is 1.
Mm-hmm.
Now we've shortened that to cis, right?
Mm-hmm.
Okay. Okay, so let me say, okay. Let me just call it theta like this because I don't want to mess with that.
So just for review.
Yeah.
So it's cosine theta plus I sine theta.
Yes.
Okay.
Yes, that's what the I means.
Yes.
CIS.
Yes.
So we have IT and CIS. So we're in the wrong department here. All right. So and IZ is equal to cis of what? Well, what's I? Well, in polar form. What's the polar of I?
Zero?
No. Well, what's the radius of I?
Yeah, one I is here.
Yeah, so the radius is 1, right?
Mm-hmm.
So, and what about the angle?
90.
No, we don't use those. We don't use those.
So
Pi over 2. So IZ is cis pi over 2 times cis of theta. So what's that equal to? What happens when you multiply two cis's like that? Well, you guys are so old.
Oh, doesn't it double the angle?
Almost.
Squares it.
No. It adds them. It adds the angles.
Okay.
All right.
I knew it did something.
Yeah. Theta plus pi over 2. So that means, so the absolute value of IZ, what's the absolute value of IZ? What's your R here? It's still 1. Okay. So that means that IT is contained in the unit circle. Because you take anything in T, multiply by I, it's still in T. Mm-hmm. So IT is contained in the unit circle. Now, by the same way, you can also show that the unit circle is a subset of IT. So IT is equal to T. All right, so we didn't change anything. Let's try something else. So here it says this was example A, and here's example B. Let's do example C. Let's just try a stupid thing. Okay. It insists. Okay. Let's take W is equal to 2. All right, so let's think about 2t. Now 2t is what do? You take any number in t and you multiply it by 2. Mm-hmm. All right, so I can draw a picture. I'll try. So here's t. There's t. Okay. It's just not going to cooperate. Maybe I can actually do one of these. So here's t. Oh, that's good. That's t. And what are you doing? You're taking any number in t and multiplying by 2. So you bring it out to 2. So you expand it. You're just expanding it. So you're just going to get, I don't know if I can do this, but I'll try. You're just going to get a bigger circle with twice the radius because you're expanding everything out. So 2t is the circle of radius in the complex plane. Okay. Now, what about 3t? Is the circle of radius, right? And so on, right? So in general, if I have a real number, RT is equal to the circle. I should say positive real number, right? RT is the circle of radius, or of radius R. But we're not done, because the cosets mean I can multiply any complex number by T. Then WT is equal to the circle of radius what?
R.
Well, here I'm talking about W, so R is no more. When you say R, what does R mean?
RT.
Well, RT, that was the previous example. Here I said if R is a positive real number, R has nothing to do with W.
Okay.
Let me write down the answer.
W.
The circle can't have a complex radius. It has to have a positive radius. So the conclusion is that the left cosets of T in C star are the circles are let's say all the circles in the complex plane with center what? What's the center of all these circles? No, what's center 0? And then homework, how about the right coset? Now you can just look through my argument and see, does it still work? Or you can use there's a property that you can use anyway. But I wanted to go through the process of looking at the subgroup, investigating what the cosets are, and then making a general statement about characterizing the coset. So that would be H. I got my work cut out for me. Let's go. All right, so now we go to 10.2. 10.2 B, D, and E. Let's go back. 10.2. So next section. How do I get to the next section?
Ron, can I ask a quick
Yeah,
question?
sure.
The one you just did for 10.178.
Yes. Yes.
Are you saying that's H, and we're supposed to take that logic and apply it to the right cosets? Is that
Well, I guess what I'm saying is that the question asks for the left cosets
right?
and the right cosets
Okay,
of T.
all right.
So you have to answer the same question for right cosets.
Okay, I understand.
Just so what you should do is go through and see, does anything change in argument.
That's clear.
All right, so let's go. So now we're going to 10.2.2D. So let's go ahead and do this. And we'll rename this. Okay, and let me see if I can clip this. Go to next.